Okay, hello everyone and welcome back to your YouTube channel. And welcome to this very exciting video. And this video today is regarding modal analysis applied to electrical power systems. You must remember that modal analysis is a very specific technique that we use for assessing for investigating small signal stability. And this is basically a technique that is based on the linearized model of the electrical power system. Modal analysis is basically taking the linearized model of the electrical power system using the state representation. And from there, we have this amazing state matrix. The state matrix A is basically the matrix defining the oscillations of the electrical power system. The state matrix is probably the most important matrix for defining the oscillation modes. And this modal analysis is basically taking this matrix from there applying what we know as the eigenvalue calculation. The eigenvalue calculation will give us the eigenvalues or the oscillation modes. If those modes can be used to investigate and to define the behavior of the electrical power system. And in this video, I will show you how to use this modal analysis functionality inside DIgSILENT PowerFactory, and we will do this using the example that we have been using for a while. That example is basically the example of a single machine connected to an infinity bus, okay? That is the example that we have been using for a while. Well, let's go for business and let's start with the test system. The test system is the system that we have been using for a while. And in this system, as you can see over here, we have a synchronous generator. And in this machine, we are using the classic model for Trostian stability, and that is basically the model using a constant voltage source behind the impedance, okay? That is the classical model, okay? And in this case, we are using the classic model for this synchronous machine that is connected to this 11 kV bus bar, and from there we are using a step-up transformer to go to 232 kVs. And this is the high voltage side of this transformer, 232. We have two transmission lines, and those transmission lines are going to a very large power system. So large that we can assume that is an infinity bus, okay? An infinity bus means that we have constant voltage, we have constant frequency, and we have a fixed angle. To be honest, the infinity bus bar, in this case, we are using as reference, and that is the reason that you can see here, 1 per unit is the voltage magnitude, and 0 degree is the voltage angle, okay? Well, we have here this very interesting and a very amazing system. We have been using this model for quite a while. We have here the initial conditions. You can see that the power delivered to the infinity bus bar, the power satisfy a power factor of 0.8 lagging power factor, okay? But what is my job now, okay? My job now is I will use a very specific calculation functionality inside DIgSILENT PowerFactory. PowerFactory has a functionality that is defined for modal analysis, and that is the command modal analysis, C-O-M-M-O-D, okay? Well, in this video, I will use this very specific functionality of DIgSILENT PowerFactory in order to assess the modal analysis. It will be used to calculate the oscillation modes, or in other words, I am using the modal analysis in order to define the small signal stability. When we use this modal analysis, the good news, when we use the modal analysis, PowerFactory is making some amazing activities for you. There are several important tasks. In this case, PowerFactory is doing very important tasks for you, okay? Because internally PowerFactory is calculating the state matrix, okay? When you use the modal analysis, you must be careful because PowerFactory is calculating for you, is defining for you the state matrix, okay? You must be careful, okay, because this state matrix that is defined inside PowerFactory is a numerical state matrix, okay? I will not go more in details, but you must understand that when we are using a software like DIgSILENT PowerFactory, there are different ways to define the state matrix. One of them is using numerical approximations, okay? And then when we have the state matrix, PowerFactory calculate the state matrix for you. Well, then what we need to do is, when we use this modal analysis, PowerFactory is calculating the eigenvalues of the state matrix, okay? PowerFactory is calculating the eigenvalues, and that means the modes. And when PowerFactory calculate the modes, as a consequence, we know the frequencies in hertz, the oscillation frequencies, and we know the damping coefficients, okay? And that is two very important variables that we need inside the modal analysis. In the previous video, if you remember the previous video, I used time domain simulations, and from those time domain simulations, I calculate the oscillation frequency, and also I calculate the damping coefficient, okay? Well, I didn't calculate the damping coefficient. I asked my students to do that at home, and I hope all of them, they were extremely clever and they were able to calculate the damping coefficient, okay? But when you are using the modal analysis functionality inside PowerFactory, PowerFactory is doing all of this for you, okay? And that is extremely important. But now I need to teach you in a very simple way how to use the modal analysis functionality inside PowerFactory. And to be honest, it's extremely simple, okay? To be honest, here you have the 4 basic steps. If you want to do 4 steps, or if you want to do only 3 steps, okay? The first step, especially if you are using the very old version of DIgSILENT PowerFactory, is executing the load flow and calculate the initial conditions, okay? If you are using the very old version of PowerFactory, you must do this step number 1. If you are using the very old version of DIgSILENT PowerFactory, for instance, the version 15.1, you need to do this. If you are using the version 2021, no. If you are using the version 2021, you can go directly and you can calculate the eigenvalues using the modal analysis functionality inside PowerFactory. And then you can print up the results using the eigenvalues analysis. You can use that. You can do that using the output window, for instance. You can do that in the output window. Or also, if you want, you can create a plot, okay? You can use a plot, and very specific plot, to show the eigenvalues, okay? There is a very specific plot. If you go inside PowerFactory, there is a very specific plot that we can use to plot the eigenvalues. I will show you that in a minute, okay? But what is important for you is that PowerFactory allows you to have a look and identify the location of the different eigenvalues using a graphical representation, okay? Then, if you want to do the step number 2 using PowerFactory 2021, you can analyze the eigenvalues. You can analyze the eigenvalues by using many tools. For instance, PowerFactory include what we call the participation factors, okay? Participation factors, if you remember my class, is one way to estimate how important is one specific oscillation mode in the whole oscillation, okay? How is participating a state variable in one oscillation mode, okay? And finally, if you are really interested on this and you are using version 2021, you can compare with the time domain simulations, okay? And we already did this. To be honest, at the very end of this video, I will compare the results coming from the time domain simulation. I will compare those results coming from the time domain simulation that I did in the previous video. I will compare with the modal analysis to show you, to demonstrate that everything is properly done, okay? Okay, what is the next step? The next step is I will go to PowerFactory and I will open the system that we already create, the system that is for this very specific example, okay? And I will do that straight away. And here we are. We are here inside the test system, and this is the test system, the single machine infinity bus bar. As you must remember, we use this file for the previous video, okay? We use this file, this test system in the previous video, and I show you about the RMS simulation, okay? You must remember that this example has 3 different static cases. This static case 0 is the base case. Then in the previous video, I show you how to obtain the time domain simulation, how to use the time domain simulation to calculate the frequency of oscillation. And today I will use the same system, the single machine infinity bus bar, in order to obtain the eigenvalues, okay? And from the eigenvalues we will conclude about the oscillation frequency and the damping, okay? What I will do now is initial conditions, because again what I want to show you is that we are using the proper test system, and one way to examine this is looking over here. You can see over here, and this is 60 megawatts arriving to the bus bar, to the infinity bus bar, and you can see that the power factor here at this bus bar is 0.8, and this is a lagging power factor. And if you remember from the previous calculation, 0.75 per unit, that is the current going from the generator up to the infinity bus, okay? What I will do now is we want to do a modal analysis, okay? And for that I will activate here this static case that is called eigenvalues. The static case number 2 is called eigenvalues, and as you can see at the top here, at the tool bus bar, you can see that the modal or eigenvalue analysis functionalities, they are enabled here. We have enabled in this static case the modal analysis or the eigenvalue analysis, okay? And here we have 1, 2, 3, 4, 5 icons, okay? What is the first icon? The first icon here to the left is the most important icon, because that icon is defining to you the modal analysis. That is the command modal analysis, okay? When you click over there, you will see this. PowerFactory will show you this window. This is a message window, and you can see that in basic options, you have some configurations that you can do, okay? For instance, the first configuration is selecting selecting the calculation method, okay? PowerFactory has two different ways to calculate the eigenvalue analysis, and that is using the QR method or QSet method, okay? That is by default the calculation method used by PowerFactory. If you want to read more about those methods, please go to the user manual, and there is a full explanation about that, okay? And the second option is the Arnoldi method. The Arnoldi method is a selective method. Is specifically used when you have some eigenvalues that they are difficult to find, but the Arnoldi method is called also selective methods because you need to define an area inside the eigenvalues plane where you assume that those eigenvalues are located, okay? We will not use the Arnoldi methods or selective method. We will keep the basic QR method, okay? We will not change any configuration over there. Then we have here the algorithms to calculate the eigenvalues. We have the left eigenvalues, the right eigenvectors, the participation factors. Then we have here some information about the results, outputs, and so on, okay? One interesting thing here, if you are a control system engineer, you must know that you are interested on having the results of the state matrix, okay? And DIgSILENT PowerFactory a few years ago include a very interesting functionality, and you can select here to have the state matrix using MATLAB files, okay? That makes your life easy. People from control system, they use the control system toolbox inside MATLAB. They are very knowledgeable about that, and they want to have the full state matrix of the power system. And to do so, people from DIgSILENT Germany, they have included this functionality that allows you to export the output file for the system matrices, okay? In this case, we are receiving the four different state matrices A, B, C, and D. For more details about A, B, C, and D, please go to the user manual or also go to my videos about theory, and you will understand that the state matrix is A, then we have B, C, and D, and all the information about that. Coming back to my explanation, I will go to basic options again, and in basic options, we will keep the default, and right now we can press here execute, okay? As you can see, when we press execute, PowerFactory is telling you that we are selecting the eigenvalue, initiating the modal analysis or the eigenvalue analysis. PowerFactory internally calculate the initial conditions. You can see that this is not like the old version. If you are using the very old version, the 15.1, you need to calculate these initial conditions, okay? Version 2021, the most recent version, 2021, is calculating already for you the initial conditions. That is the reason that I say in the previous presentation, don't do that. You don't need to do that. Then PowerFactory is checking the input signals because you need to put some inputs inside the model in order to get the state matrix. Then PowerFactory is telling you that the state matrix, the system has 3 state variables and 27 load flow variables, and then 3 eigenvalues are calculated, okay? And there is something very interesting. PowerFactory is telling you that one of the eigenvalues is not calculated, is not included because it's not inside the limits, okay? Finally, you have here at the very end, echo in the output window telling you that the modal analysis is successfully executed, okay? What is the next step? The next step is my students, they want to see the eigenvalues in graphical way, okay? You can do that in a very simple way. Let me maximize here the size of the graphic window, and I will include here, let me do the following. I will create a plot, and in this case, I will create a plot of eigenvalues, okay? You can see that when I select here at the toolbar, I select here, create a plot, PowerFactory is going directly to Modal eigenvalues analysis and selecting by default eigenvalues, and you press OK, and PowerFactory will ask you the following, okay? What is the name of this new plot? If you want to show the stables and unstable eigenvalues, PowerFactory is so clever that it will show you the eigenvalues with colors, and green color means stable eigenvalues, and in red color you will see the unstable eigenvalues, okay? And I will select this by default, everything is fine, and I will say okay. And right now you can see something quite interesting, okay? You can see that here there is a cross here on the top, and there is another cross here at the bottom, and those crosses represent two stable eigenvalues, okay? Two stable eigenvalues, as you can see here, they are complex, they are conjugated. The real part of those eigenvalues is negative. You can see that we are on the left side of the plane, and this eigenvalue is having a real part negative, but is also having positive and negative complex or imaginary part, okay? And now what we can do is we can select one of these, okay? I will try to do this, select, and then we click on the top of the eigenvalue, and PowerFactory is showing me the information about that specific mode, okay? When I click here on this cross on the top, you can see that this eigenvalue is the mode number 1. That is the mode number 1. You can see the real part is minus 0.17, and the imaginary part is 6.89, okay? You can see here the damped frequency 1.096, and you can see that the period is 0.91 seconds, okay? That is very valuable information. And then you can see over here the damping ratio, and the damping ratio in this case is 0.0025, okay? You can do the same here with the eigenvalue at the bottom. I will try to do it because it's quite tricky. You need to select the eigenvalue. You can see the small cycle over there, and then click, and you can see this is the eigenvalue number 2. You have the real and imaginary component, and then you have the frequency and the period, and finally the damping ratio, okay? There are no surprises here. The oscillation frequency is the same, and the damping ratio is the same, okay? However, if you want to have a full picture about the whole set of eigenvalues for this system, PowerFactory is having here at the top, at the toolbar, it's having an icon that allows you to create a table, and that table show you all the information about those eigenvalues. And that is what I will do now, okay? If you press over there, PowerFactory is asking you, okay, you want a table, but what kind of results do you want in that table? And you can select here between modes and states. And for simplicity, in this case, I will select modes, okay? And you can see over here that PowerFactory is showing me that we have two modes, okay? Mode number 1, mode number 2. Both modes have the real part negative at 0.017, and we have here the imaginary part. You can see that the mode 1 have positive, and the mode 2 is minus 6.89. Oscillation frequency is the same for both modes, 1.096. And you can see here the damping ratio is the same for both of them. You can see that is 0.025, okay? That is just basically to show you that we can use DIgSILENT PowerFactory functionality for modal analysis, and we can successfully identify oscillation modes of this system, okay? And that is extremely, extremely important. What I will do now is I will come back to my PowerPoint presentation, and I will show you more details, okay? Let me go back to my presentation. Right now we are here at my presentation, and as I say before, I can use the table form in order to assess the eigenvalue analysis, okay? In this table, PowerFactory is showing me that there are two oscillating modes. And those modes, you can see over there, they are basically one on the top. That means is a positive, real component, imaginary component, and then we have another mode with a negative imaginary component. But the important part here is that we have the same oscillation frequency, but also we have the same damping ratio, okay? And you can see here, I am highlighting here, the oscillation frequency is 1.096. And here you can see the damping ratio, and the damping ratio is 0.025, okay? Now it's time to show you the most important part, okay? The most important part is in my previous video, I use something that is not quite typical, but I use the time domain simulation in order to show you the electromechanical oscillation. Using the time domain simulation, I show you the response of the rotor angle and the rotor speed. Using the time domain simulation, I got the plot, and I used that plot. I used some signal processing calculations to obtain the frequency, the oscillation frequency, the frequency of oscillation of that signal. And then I use modal analysis. And what is the very nice surprise? Well, there is not a surprise. What we can see over here is if we calculate the oscillations, we can see that the frequency using the time domain, the frequency of oscillation using the time domain, it was 1.0989 Hertz. That is the result that you can see here at the bottom, okay? Here at the bottom, I present the results. I am presenting the results using the time domain simulation. The plot that I am showing here below, is basically the plot coming from the rotor speed, okay? And you remember that in my previous video, I used this plot to calculate the frequency. And that was extremely simple, to be honest. It's just calculating the period of this signal, and from the period you can calculate the frequency as the inverse of this specific frequency, okay? What I'm telling you is this plot over here is the time response of the rotor speed, and we calculate here the frequency, okay? We use this approach of using two consecutive peaks, and from there we obtain this period, okay? And the frequency was 1.098. If you look over here at the top, I use the modal analysis. We use here modal analysis, and the modal analysis is giving me two eigenvalues, two oscillation modes, and you can see that the frequency, okay, the frequency is 1.0969. Some of my students, they will say, okay, professor, this is not similar, this is not 100% match. But what is the problem? That here I am using a very simple way to calculate the period, okay? The period in this case, my manual calculation says 0.91, okay? And if you compare the period, you can see over here, the modal analysis is giving me the period. And the period in the modal analysis is 0.9116. My difference between my manual calculation and the modal analysis is coming from these results, okay? PowerFactory is taking all the decimal points, and as a consequence, it's giving you a more precise value for the oscillation frequency, okay? And that is the case. That is the case. We are receiving a frequency of 1.096, and that is coming from an oscillation that is having a period of 0.9166. Okay. Well, from there, I show you that you can use the modal analysis. You can use the modal analysis, and you can use the time domain. Here at the top, we have the results. This is the results coming from modal analysis, okay? And here we have the result from time domain. And what we have shown here is that there is some similarity in the results, and we can get almost the same, okay? Well, this is all for this video. We are almost finishing this here, and this is the end of this video. I show you two different ways to calculate the oscillation, the frequency of oscillation in this very small and practical system. We have used those methods, and we compare the frequencies, okay? I highly suggest to my students, if they are interested to learn more, please go to the following reference, okay? I highly suggest that you can go to the Condor book. Condor book is having Power System Stability and Control book of Prabha Kundur, is having a very well and very nice explanation about modal analysis. Specifically, I think it's chapter number 11. I'm not completely sure, but I think it's chapter number 11 is showing you basically the modal analysis. But also this book, Computer Modeling and Electrical Power Systems of Josh Arrillaga, I highly suggest. Also, P.M. Anderson is having a very good explanation about modal analysis. And finally, you can find some very good explanation in this very interesting PhD thesis of 2006. There is a PhD thesis coming from the Swiss Federal Institute of Technology in Zurich in 2006, and the title is Use of Fax Device for Power Flow Control and Damping Oscillations in Power Systems. If you have opportunity, I highly suggest that you check all those for different reference and have a proper look and understanding more about modal analysis. Well, this is the end for this video. Thank you very much for watching. This is the end of this video. In this video, I show you how to use the modal analysis functionality inside DIgSILENT PowerFactory. You can use that functionality in order to calculate, in order to obtain the frequency of oscillation, the damping ratio, and more information, okay? This is the very beginning, okay? Now it's time for my student, my master students, that they take independent learning, and they can go and read the 4 different references that I showed before. They have a proper understanding, they can be very reflective, and they can start to use better and deeper DIgSILENT PowerFactory. For now, that's all. Thank you very much for watching this video. Please, if you want, subscribe to my YouTube channel, and also a like to the video will be nice. Thank you very much for watching, and I will see you at the next one. Thank you very much, and bye now.